So we have a great, an interesting transition from Pat's tour de force of the global issues and complexities. I'm going to focus on North American system, the iconic Gulf of Mexico, Chesapeake Bay, and Lake Erie. And it's been a really great experience to actually be able to work in all three of these areas and compare them. I'm also going to probably violate at least 3/4 of what Pat said in what we actually need to be worrying about in building these models, because I tended to use some very simple models that are looking at very gross properties, and so we're going to interpret some of what I'm saying carefully as we're going forward. I'm going to start with the Gulf of Mexico and talk a little bit about our resurrection of the old Streeter-Phelps equation and how we use that in a simple way in the Gulf. Its transition into Monte Carlo and Bayesian frameworks, and then our use in scenarios, forecasts, and then to show our track record over the last dozen years or so. Then move into the Chesapeake Bay and how we adapted that Bayesian Gulf model there and use it to help identify and think about the impacts of regime shifts and what's happened in the Bay. And again, looking at scenarios, forecasts, and the track record. And then moving into Lake Erie, where we used a more classical food web approach to hypoxia, some Bayesian analysis and forecasting for harmful algal blooms. And again, their use in the scenarios, forecasts, and applications. And if I have time, I want to talk about our watershed work on Lake Erie. The context here is that this kind of modeling is the interface between the environmental impacts that people care about and the loads that drive them. And we really have to sort of use these in these tools, which is why I focus on scenarios and forecasts, and particularly on their track record. We'll start with the Gulf of Mexico. The context that we were working with when we were doing this analysis is that was the hypoxia record that we had starting only in 1985 going forward. Yet the nutrient load change, nitrate particularly in this area, had that sort of a track record back to the 1950s, and land use in fertilizer applications changed on this scale. And so looking at this particular time scale, the first question that had to be asked was, well, when did hypoxia start in the Gulf? Has it always been there? And what are the sort of the scales we ought to be thinking about? So the two big questions that we were wrestling with back at that time was, when did this large-scale hypoxia start? And a corollary to that is, what would be a reasonable restoration goal? And then secondly, what's the required nitrogen load reduction to get back to that goal, or to those conditions? And there were models being developed, three-dimensional ecological models, very complicated models that were sort of exploring how the system worked. But I asked the question, can we actually think about the coastal current in the Gulf of Mexico as a river and model it in the old Streeter-Phelps model of a DO-sag curve, where classically, let's see, there it is. The river's flowing downstream, you dump in organic matter, oxygen declines and then comes back up, the organic matter decays. Can we think about modeling the coastal Gulf of Mexico in that way? Well, if you look at it, this is the sort of the typical size of the hypoxic zone, starting from the Burfoot Delta, heading out towards Texas. It's 500 kilometers long, 50 kilometers wide, and about 10 to 20 meters thick. So it's kind of like a river. If you look at the physical oceanography, the coastal current is like orders of magnitude higher than the cross-shelf current. So it kind of functions as a river. So the simple river model, as I had mentioned, is you're dumping BOD in. It decays, and as it decays, it uses the oxygen. There's diffusion across the surface, and it moves downstream. And so in our case, we said, well, let's look at the Mississippi load of nitrogen as a surrogate for the BOD load. The diffusion now is across the picnic line, and it moves downstream. In the case of the Gulf, we actually had two loads, right? We had the Mississippi coming in, and then later on down the stream, the Atchafalaya comes in. So we put this model together and just tried to see whether or not it would work. When you solve the equations, it said steady state, you have the load, the oxygen decays, it starts to recover, the second load comes in, and the same thing happens. So if you have different kinds of loads, in some cases you'll get no patch, there'll be no hypoxia anywhere along the ways. If you define hypoxia as this black line, some cases you'll have two patches, and then some cases you'll have a long continuous patch. We'll come back to that in a second. What's really nice is that you're actually modeling concentration along the spine of hypoxia, and there's a really nice, strong relationship between hypoxic area and its length. And so if we could actually predict the length of hypoxia, we can get an estimate of its actual area. So this is the equation, this is the solution to that model at steady state. There are three coefficients that are involved. The decay rate of the organic matter, this downstream advection that I'll talk about again a little bit later on, and then they're mixing across the picnic line. This advection term, the physical oceanographers hated it when we first published this stuff because they did a quick calculation and said, well, that term that you're using for advection is not realistic at all. It doesn't actually work in the real world. But really, this is really just a calibration term. It accounts for the surface flow, the sedimentation, the subsurface flow, and all the ecology that we're not modeling. So it's a bulk calibration coefficient as we move forward. So what we did was we held the other two coefficients constant, and then varied V for each of the individual years to see whether or not we can match those observations. And if you look at length and area from 1984 through, I guess it was 2011 at the time, we could get a really good fit by adjusting that coefficient each year to make it match. So it's a sort of year-by-year calibration. And we're looking at some of the validation, looking at the location of the patches, some of the cross-picnic line flux observations, and the oxygen consumption to see whether or not the model is working well internally. These black lines represent the observed length of hypoxia, starting from the Birdfoot Delta and moving out towards Texas. So these were the observations, and this is what the model said. So we did a pretty good job of putting the dead zone in the right spot. In places where there were two patches, we found two patches, and so we were pretty happy with that. This is also a set of observations that Dubravko Justic and others did, looking at cross-picnic line oxygen flux and oxygen consumption below the picnic line. The time series during the year are their observations. We were modeling midsummer conditions, and that's what came out of the model. So we were doing a pretty good job of matching the internal processes as well. So we got into the situation where now we want to do some hindcasts and ultimately do forecasts. But the problem is we don't know what a historical V is, and we certainly not going to know what it is in the future. And this came to us when we did our first real forecast. This is what we forecast as the sort of the spine of hypoxia in 2003. When you superimpose the actual observations, it looked like that. And what happened was a whole bunch of tropical storms came through and hurricanes came through just before the crews went out to do the observations, and it broke up the hypoxic area. So you really can't predict in the sense of deterministically because you don't know what that V is going to be. So then we moved into the Monte Carlo simulations instead. And in this case, what we did was we used the mean and the standard deviation of the 17 years of V's that we did in the calibration. And we just picked 1,000 values from the mean and standard deviation distribution and ran Monte Carlo simulations across the system, and then looking at the first and third quartiles as a comparison. And if you do that, so this is the observations that we have from 1985 on, the red boxes. The error bars are the mean, plus or minus the first and third quartiles from the Monte Carlo simulation. So we can reproduce it in a statistical sense in doing this. And by having this, we can then actually start asking these questions. So when did it start, and what do we need to do for loads? If we had the loads going back to the 1950s, so we drove this model using this Monte Carlo approach historically, and from that work it suggests that large-scale hypoxia really didn't start happening until the early 1970s, and these were sort of typical values of maybe 5,000 square kilometers, which, by the way, turned out to be the goal set for the action plan. We can also then run the model in another way, looking at the area as a function of the percent load reduction and using these first and third quartiles from the Monte Carlo simulations to produce a forecast envelope in this scenario mode. And the action plan that was created did say 5,000 square kilometers was a good way to shoot for, and it suggested a 35 to 45% load reduction, which of course everybody's coming up with 35 to 45% load reductions no matter where you are, and that's because the loads have tripled during this time period. Anyway, so that was what we ended up doing here. What was interesting then, this is sort of the first time we moved into this multiple model approach where Dubravko, Justic, and Vic Bierman also had models, so we could compare what the three models were telling us about those same two questions. So this was, I had already shown you my results. This is bottom water oxygen concentration simulated from Dubravko's model. Here is the hypoxic area, and it turns out that ours suggested that it started in the early 1970s, and the oxygen concentration did this big decline during the same time period, according to Dubrovko's model. So it's a nice confirmation, at least from two very different kinds of models. In the forecasting world, so ours suggested this 35 to 45% reduction. Vic's model was a multiple box hydrodynamic model in the ecological model, and he was looking at the change in the percent increase in oxygen in the bottom layers as a function of the load reduction. And if you compare those, that 35 to 45% said that there would be about a 50% increase in oxygen concentrations in the bottom water. So again, two very different models giving us interesting common results. So these suite of models have been used. They were used extensively in the policy world. The original integrated assessment started this whole process. The first action plan, the EPA Science Advisory Board assessment of the action plan and the science, and the revised action plan have all used this suite of models and confirmed over and over again the 35 to 45% load reduction is what's going to be needed. The latest one, based on the EPA review, said don't just worry about nitrogen, you need to do 45% reduction in phosphorus as well. So they were listening to you. We've also been using these as blind forecasts every year. So every early June, we forecast what the hypoxic area is going to be in August. And we've got now, I think, 12, 13, 14-year track record of the predictions, which are black, and the observed are in the blue. So we're doing a pretty good job. We fail in a couple of cases pretty significantly. And in both of those cases, the actual observation was a lot smaller than our prediction because the hurricanes came in just before the observation crews went out again. So we can understand that. Two reasons why we do these annual forecasts, and we also do it in the Gulf, in the Bay, and in Lake Erie, because nobody can really use these forecasts if you think about it. We do it for two reasons. One is every year the policymakers have got to answer questions because the press picks it up and starts making a big deal about it's still a dead zone out there. So it's a good policy driver for that. And then the second reason is if you actually build a track record that looks pretty good over time, you have more confidence in using these models in scenario mode, which is the ones that we're using ultimately to try to set new loading targets. So now let's move on to moving north to the Bay. Very different system, but we thought we would try it again there. Now this is the looking downstream. The Susquehanna comes in up here and moving downstream, the cross section, and sort of the profile. And of course, the BOD, the load in the Bay, comes in mostly here, but other places along the way. It comes down, rolls down the river, and then because an estuary, the flow is actually back upstream. And so we had to change the model a little bit. We dumped the load down there and then modeled it flowing back upstream and below the picnic line and got profiles that look like this. So we're able to match across a large number of years these sorts of profiles. One of the interesting things in the Bay is that the length of that hypoxic area is very nicely correlated with the volume. These are from observations, and so we can predict length, we can actually get volume from that. And this was, again, using the same thing where we adjust V every individual year, so it's not really good practice, but it's a way to see whether or not the model is working itself. And an R-squared of 81% between models observed and predicted volumes. So we did the same thing, sort of Monte Carlo analysis to get the error bars in the model, and this is where we started getting ourselves in a little bit of trouble. If you look carefully at the dark black dots, those are the individual years, and the model didn't look very good in looking at the individual years, so we thought, well, let's look at bins, and it started to look better that way. So we're thinking that we're getting somewhere. But then we looked a little bit closer at it, and what's really happened here, these are now the observations of hypoxic volume as a function of load. And there really were two different classes of data. There were data that were from the 1950s to the 1985, and then data that were 1986 and 2000 to 2006. So there was something happening in the Bay that was changing the relationship between the hypoxic volume and the load. So we switched at this point into a Bayesian framework for the model, so we could actually use the analysis to estimate the coefficients of the model based on the observations and not based on our own hand calibration. And you can do it individually and let these coefficients vary from year to year, so it can tell you something about what's happening with the structure of the system. So what we have here is These are the Bayesian-based estimates of that V coefficient. D sub I is the initial oxygen concentration in the beginning of the model, and F is the fraction of the organic matter that actually settles below the picnic line. These are coefficients in the model, and we let the Bayesian analysis pick it, and what it showed us was that something changed here and here and here at the same time period. And in looking at what was in the literature at the time, this calibration term that shifted upward after 1985 was likely reflecting some change in the benthic ecology that had been reported by others during this time period as a result of repeated hypoxia. This change in the initial oxygen concentration, and more importantly, the fraction of the surface production that gets below the picnic line, the decrease there is consistent with the fact that over this time period, the surface production of algae in the bay moved southward. And so what was happening was a lot of the surface production was moving outside of the regime of the model. Our model stopped, or actually started at the Potomac. So therefore, the fraction that's settling would actually be decreasing. So the model was telling us what these changes were, and the changes in the coefficients were actually being reflected in what we knew about the system itself. But then we were left with a really interesting problem, and that is, well, here's the model results using the early data, and the model results using the later data. Which curve do you use for your scenarios? Because you get very different results. Do you believe that if you're sitting in 2006 or 2010 and you reduce the loads to what it used to be back in the 1960s, is the system going to revert back to the 1960s curve, or will it stay on this curve? And you really don't know. So you had to make a choice. So we've got two applications of this. The first one is, so there has been a TMDL set for the Chesapeake Bay, and so we know what the loads coming out of the Susquehanna will be if they reach the TMD loads. And so we ran the model for these years, 1991 to 2000 cases, and this is what the hypoxic volume looked like under the current load conditions, and what it would look like if they ever reduce it to the TMDL loads. And it showed that about a 50% reduction in volume. We've also done track record. This is an example of our annual forecasts, and we are assuming that we're following the path of the later years in the model. And in our track record, we've been doing this since 2007. And again, we're doing a pretty good job of doing these blind forecasts, with the exception of these two odd years where the weather over the estuary actually matters. And it was one of these cases was a hurricane that came through and mixed up the water. So there's a limit to what these models can do. So now I want to finally move all the way up here to the Great Lakes and switch and talk about hypoxia in a freshwater system. You can't use this river model because this is essentially a vertical system. So we really couldn't do that. So we reverted to a more traditional approach to doing that. And I just wanted to, for scale, for those of you that are not from this area, this is Lake Erie. This blue area is the frequency of the hypoxic area in the Central Basin. This is what happens 20% of the years. And this is what happens in 40% of the years. And for scale, this is 8,000 square kilometers, 10,000 square kilometers. The entire surface area of the Chesapeake Bay is about 11,000. So this is a pretty big area that we're dealing with. And our charge, what we were looking at, is under the new Great Lakes Water Quality Agreement, they have to set new target loads for Lake Erie, and we're trying to help develop the models for that. In this particular case, this is our model. There were a group of other models. Lewis is back here. He was part of this project. One of the models that we used was a vertical model that started with a vertical mixing model, so we could get temperature and the mixing regimes correct. And then we implemented sort of a standard NPZ model for this, looking at, again, phosphorus-driven. Phytoplankton, zooplankton, oxygen, and sediments, and with multiple layers in the model itself. The calibration in this time, what I'm showing here is the comparison from 1987 through 2005 was when we did this work. The red dots are the observed dissolved oxygen in the epilimnion and the hypolimnion, and the solid lines are the model. So we actually be able to model the depletion of oxygen pretty well in each of those years. So we use this. This is the plots now. And we also ran this model we had 17 years of observed meteorology for the system. And so we were able to run this model for 17 years of meteorology to look at the interannual variability that drives the system. So that's what the error bars are this is what the bands are in the model, and the error bars on the actual observation. So area, we can look at hypoxic days, the depletion rate, and the bottom oxygen concentration. We used this along with other models. So there are 3 other models that were being used in this experiment that we're doing for the Environment Canada and EPA, looking at the relationship between hypoxic area and the load to the central and the western basins. So these are the 2 versions of the model that I was just talking about that we did. The others are here. And from this, we looked at the ensemble, and we were able to make a recommendation of what the loading target ought to be in order to meet this hypothetical, in our case, 2,000 square kilometer goal that we had talked about. We also had another group that working on the toxic algae in the western basin, and so we had some models that were developed looking at that. And I'm not going to show you much of the details. There are 3 different versions of this. Rick Stump was the first one to develop a very simple regression model that relates the spring load from the Maumee River as a function of the toxic blooms with different assumptions and different error bars. This is the actual curve here. Isabella Bertani and others in my lab did a similar regression, but found that there was a time term that mattered, that in fact the system was becoming more susceptible to these blooms over time. And so you actually end up with 2 different kinds of curves, like we had the problem that we're trying to deal with in Chesapeake, that we have one curve representing the earlier time period and a new curve representing the current time period. Then Ed Verhamy and others at Limnotech had a detailed, complicated 3-dimensional ecological model of the Western Basin, could generate the same sort of response curve. And if we looked at all 3 response curves, we got and set a similar response variable in the 3 cases, we were able to come up with a very consistent set of loading targets for harmful algal blooms in the Western Basin. So we had, I think overall, we're looking at the Western Basin, the Central Basin, some other work in the Eastern Basin, 8 different modeling groups that were doing different versions of models, looking at different parts of the problems. And when we combined them, we had put together a set of recommendations that the spring Maumee load, in order to prevent harmful algal blooms, needed to be about 32% below the 2008 level. And for the Central Basin hypoxia, the 2 recommendations, whether you're basing it on concentration or area, were in the area of 50 to 60% load reductions below 2008. I don't show it here, but we also had a recommendation on Eastern Basin Cladophora, and I'll get to that in just a second. These were our recommendations. The task force, the US and Canadian task force, uses information and other information and set these as the recommendations for public consumption. Rather than 32%, they selected 40% below the 2008 levels. They chose a different criteria for DO and picked 40% below the 2008 level as a recommendation. And they decided that the models of the Eastern Basin Cladophora were not sufficient to base a recommendation on it, so they just deferred that decision for some other time. These recommendations were sent out for public comment, and eventually US and Canada adopted them as their new targets for Lake Erie. And I guess I do have time for this. And so, like I like to tell my students, that was the easy part. Setting the loads is the easy part. Getting the loads, so getting to those loads is the really, really tough part. And this is where the watershed models are actually very critical. So I want to talk about our application of that. And we did something, again, on this idea of multiple models. We brought together 6 modeling groups. Each modeling group had previously developed and calibrated a model to the Maumee watershed. So we had these 6 independent models, but not quite independent models. And we're going to ask those models all the same questions and see what kind of range of results we're going to get. So these were the target loads that have now been set. The question is, can we get to those targets? And if so, what practices do we need to play in the watershed in order to get there? So these are the groups. There was my lab here. If you have any questions about SWOT, I brought my answer people with me. A group from Ohio State, Heidelberg, Limnotech, and USDA, all running different versions, different implementations of SWOT and then the USGS Sparrow model. Dale Robertson was part of this team as well. In developing this, we worked very closely with conservation organizations, NGOs, and agricultural community to get them engaged in the process, to have them help us decide what kinds of scenarios to run, what kind of practices do they think are feasible and worth exploring. We still got beaten up at the end, but we actually engaged them in the beginning, which is an important part to do. So 5 of the 6 models were SWOT, and I'm going to focus mostly on SWOT results here because I wanted to look at the scenarios that you can run for different practices, and Sparrow could not do that, but Sparrow was involved in other parts of it. So why SWOT? There's lots of different ways of doing this. There were 3 different reasons. One was it was a USDA developed model, so there's some sense that the ag community might be more accepting of the results of that model versus others. May or may not be true. But the more important thing is that it can work at watershed and river basin scales. It looks at both the quality and the quantity of the surface and the groundwater, and you can look at the impacts of land use, management practices, and climate and in the models. It's designed to do that. So you can look at alternatives in conservation tillage and waste utilization, nutrient management, cover crops, filter strips, waterways. You can actually use these sort of scenarios in that model, so which is why we chose that, because those are the kinds of questions we want to ask. Most of you probably know how SWOT works. It is based on these hydrologic response unit of common slope and soil types and others. We model plant growth, management activities. It delivers and routes the nutrients and flow, sediment through the system to Lake Erie in this case. We had this amazing 40-year data set from Heidelberg that had daily observations. And if you want to talk about constraining a model, trying to match 40 years of daily data was quite a challenge. The downside, though, is that's the only data that we had. We did not have data throughout the system in sufficient quantity to actually look at what's happening in detail throughout here, which is a real problem. Before starting, we had these, the original models that had previously been calibrated, and we wanted to develop a common baseline for all of the models. So we generated from NOAA, the meteorology, to drive all these models with the 2005 to 2014 observed loads. And we also developed a common database of point sources. So everyone used the same meteorology and the same point sources in their models. But they all had their own assumptions built into the models about what do you do with this mysterious ag data that you can't get your hands on. You have to make assumptions about that. How do you interpret the information that you have at the scale of the model? So there's a lot of variability going into the modeling, even though they all use the same basic framework. So this is the results of that baseline calibration. This is now the red dots are the observed loads coming out of the Maumee from 2005 to 2014. The target load is this red line, and each one of these sets of lines are the results of one of the different models. And so we bracket it pretty well. We also show that in some years we may already be hitting the target, but in many years we're not. What was really interesting, I'd like to think that this was intentional, but I think this is just fortuitous. But if you look at the average and the standard deviation of the models, we really hit the observations pretty well. And so either all the models were compensating for each other's errors, or there's some value in the rigor of doing multiple models. So then we built these scenarios, and we built the scenarios. We did a bunch of individual scenarios, like filter strips only or nutrient management only, and looked at the impacts of individual practices and used that part of the baseline for figuring out what scenarios to build. Guidance from the stakeholders. When we were doing targeting within the watershed, we targeted high potential phosphorus export areas. We looked at different rates of adoption. So is it 25%, 30%, or do you want everybody in the watershed to do something? And we also looked at, when we're going to convert areas out of agriculture, we always look for the lowest yielding croplands. These were the scenarios, and I'm not going to talk about them, but we did 11 different scenarios, and I'm going to show you some of the results graphically instead. So this bar graph, there's 2 of them, one for total phosphorus, one for dissolved reactive phosphorus. The first bar is the observed load during that 2005 to 2014 time period. The red line is the target that US and Canada are trying to hit. So the first bar is what happens if you remove all the point sources from the watershed. Turn them all off. So you get some effect, but it's clear we're dealing with a non-point problem. We sort of knew that, but it was important to actually demonstrate that in this context. We then ran 3 scenarios that got us in trouble from a public perception standpoint. We wanted to ask the question, how much land would you have to take out of agriculture if you didn't do any best management practices? It was a really interesting story, but of course, we got beat up for doing that. So if you took out 10%, 25%, and 50% of the land, converted it to grasslands, you could get to the target with 25 and 50%. But that was just to do some scaling for us. These were the actual scenarios. I won't go through all of them, but to point out that in 3 of them, we actually do get below the target load. And this is for total phosphorus. And it's the March through July load, which is the load that drives the harmful algal blooms. So 3 of them hit the target, but 4 others get close. When you consider the error bars from the models, and that's what these error bars are, the mean and the standard deviation of the model output. So it's feasible, or it's possible to get to that load. This is the same thing looking at dissolved reactive phosphorus, which is also considered an important driver on this system. And in 2 cases, we get to the target load. In 3 other cases, we can get close. And so the 4 scenarios that ended up within the sort of the range of getting us close to the 40%. The first one, so 3 of this one is for dissolved reactive phosphorus only. These 2 get us the total phosphorus load. This one gets us both. And what it really is here is subsurface application of the fertilizer, so injecting it into the soil rather than broadcasting it across the surface, putting in winter cover crops, and medium quality buffers on 50% of the high phosphorus loss land. That will get it both to the target. I also point out that in all of these cases, the simulated crop yields, watershed level crop yields, changed by less than 2%. So you could actually implement this and have very little impact on crop yields, according to the model. The summary of that part was that there are multiple pathways to get to this 40%. But it's going to require widespread adoption. I mean, something that we've not seen anywhere in any system, not just in Lake Erie. Whether you're talking about the Chesapeake or the Upper Mississippi, we're talking about 100% implementation of nutrient management across the system, or 50% of the system having buffer strips involved. So it's massive, massive implementation. This subsurface application is probably one of the most effective ways of doing this. In this system, that we had dramatic changes in the mid-1990s, and many people were attributing that to no-till. That in fact going to no-till, which is good for keeping particulate phosphorus on the land, was creating conditions for dissolved phosphorus to come off more readily. But it's complicated because when they went to no-till, they started doing broadcast fertilizer. So it may be more the broadcast versus subsurface application that's driving that problem. As expected, targeting is better than random placement of practices. Not all combinations meet both of those. And it is possible to get to that and maintain agriculture if you believe these models. So lessons, this was like my life for the last 15 years. Lessons learned from this that I think may be important. One is that simple models can be useful. These simple models that we put together were useful in the scenarios and the forecasts, even in exploring some of the observations like regime shifts. It doesn't give you a lot of insight on how the system's working, but it gives you a nice tool for looking at response curves. This idea of multiple models, I think this is something that's going to be really critical. There's too many places where the decision makers have got to rely on one model. And there's so much uncertainty associated with models that if you have multiple models taking different approaches, you can build more confidence. In the case, the Gulf, we had 4 models that advised the action plan. There are now 4 models involved in the annual forecasts. There are 3 models that were involved in Lake Erie hypoxia scenarios, 3 in the HAB models. These models are now also doing the annual forecast, and 6 models involved in the watershed. So convincing funders that they ought to fund multiple modeling groups is the way we ought to be going. I think these annual forecasts build skill and raise awareness of the issues, and using these annual forecasts in scenario modes actually have been successful in advising policy going forward. That's my story. Thank you. Good.
Yeah, we have time.
Time for the questions?
Time for questions, yes. Can your models shed any light into how long it will take relative to implementation to see results?
Yeah, really interesting question.
Especially of the HABs in Western Lake Erie and your marching intercept.
Yep. So, yes, but we had to be very careful about it. I'm talking about the SWAP models now. When we originally had the earlier versions of the model, I asked our modelers, I said, let's just turn off all fertilizer, stop fertilizing, and let's see how long it takes the system to respond. And we grew crops for 90 years. So we knew that was wrong. Then we looked more carefully at the phosphorus content of the soils observed in the system and made sure that the models were reflecting those concentrations. So now if you turn off fertilizer completely, the crops will only grow for 10 years, which is actually close to observed systems, observations in other systems. And that's what's shutting off fertilizer completely. So we know it's going to take decades for these systems to respond to whatever practices are going to be put in place. And I think we're seeing this in the Chesapeake, where they did put in the TMDLs. There's a lot of actions going on, but the loads are changing very, very slowly, maybe even not even detectable in terms of the interannual variability. So we're now involved in another project funded by the state of Ohio to use these same 5 models, or six models, to not just do the brute force question of turn off fertilizer, see how long it takes, but actually build in a rate of adoption over time. And then overlay that, since we're going to be looking at long-term scenarios, overlay climate projections on top of that to see how long it's going to take to actually see something that's measurable. And it's going to be a long time.
Well, given that, and I'm not trying to get you tarred and feathered, but
why not?
And given the way ecosystems respond and the possibility of hysteresis and all of this, why not suggest instantly turning phosphorus loads to 0 from agriculture, and then decide to turn it on when crop yields actually start to fall? Because the system may need a shock to change.
So you mean, we can't, first of all, you can't shut it off because it's there, right? You can shut off fertilizing. Yeah. That's why we ran that scenario. Of course, you're never going to get that in any policy anywhere. But I mean, the reason why we ran that scenario was to make the point that even shutting off fertilizer is going to take many years to see the result, and it won't impact yields. That's the part that nobody will buy.
Well, then that's what I asked the question, why not put it out there? Because it might actually...
that requires regulating agriculture, which is a challenge in both countries. Yeah.
I guess I have a follow-up and related question. Have you used these models to look at the cost associated with these alternate policies? And if so, does it vary significantly?
Yeah, so I'm going to look to my folks back there. We actually have done, we have data on what it costs to implement these practices, and you can build those into it. It doesn't always cover all the real costs, but so we can do that, and we have done that. I don't know what the numbers are, but the real problem is it's really hard to estimate the benefits. There's some work that's been done on what was the economic impact of the big toxic bloom in Lake Erie, and you have that number, but there's so many other unquantifiable impacts. I've always been worried about doing that kind of cost benefit, because I remember from my days in NOAA, there were folks there that were working so hard to figure out what's the value of an acre of a wetland. They looked at fisheries and all that kind of stuff, and they came up with a number, and a developer came in and said, I'll give you 10 times that, because it's worth that much more to put a condo on it. So without really being able to quantify the full benefits, I shy away from it. We can talk about costs of implementation, and we have those numbers.
Can you tell something about the role of the sediments and the phosphor in the sediments in Lake Erie? Because if you stop loading, there is still the sediment load going on.
Yeah, so a couple of the models that were involved here were able to look at that, because that's the internal loading part, and we didn't see a large effect at this point. We saw there were some, there clearly will be, but it doesn't really impact doesn't really impact what the load reduction ought to be. What it impacts is how long it's going to take to respond. And so we've sort of looked at the time courses of that, and we also try to avoid that conversation with policymakers because it's an easy thing for them to say, oh, but that's going to persist for a long time. But it doesn't affect what the load ought to be. It does affect how long it will take to respond. Yeah?
Great. Thank you very much, Don.